So hello everyone, this is lecture 27 for the accident in magnetism. In the last lecture we were discussing about the Faraday's law and today we will see that how change in magnetic field produces the electric field. So we'll see the magnitude. So first we have a solenoid. Inside the solenoid the magnetic field is changing and it is changing because current over the solenoid is changing. So current is given by IT as I naught cos omega t in the direction of phi, means it is over the surface, that's why. Now BT will be mu naught n I. So here I is changing, so B will be changing inside and outside will remain 0. So due to change in the magnetic field, there will be some electric field developed. So we need to see that what will be the magnitude of that electric field. So we know the relation del cross E equal to minus del B by del T. So from here we can write the integral form, that is E dot dl equal to del B by del T dA. Now we need to use this equation because here we need to see that what is the electric field. Electric field will also be in the direction of phi cap because it is along the current. So E dot dl will be given by this. So let's see, for r less than r, we consider some loop inside the solenoid. So inside it will be E into 2 pi r for this loop equal to mu naught n, and that is minus. So first it is B, how B is changing with t. So B is given by this, so you need to take the differentiation. So it will be, in place of IT you will write this, it will give you minus cos omega t, minus sin omega t and omega. So here it will be minus I naught omega sin omega t, multiply the area will be pi r square. So from here you will get the expression for E, it will be 1 upon 2 mu naught n I naught omega sin omega t r and phi cap. So direction will be along the tangential. And here you can see that E is proportional to the R, so whatever the distance will increase, the E will increase inside the solenoid. Now let's see for the outside. For outside, let's consider some loop with radius small r. So A into 2 pi r will give you minus mu naught n, and again it is dB by dt, so it will give you minus I naught omega sin omega t. Minus will become plus and this time the area will be pi r square because affected area is this of the solenoid. B is passing through this only, so that's why we have taken here capital R. From here you will get this relation for E, and it is again the phi cap direction. Now here you can see that E is proportional to 1 upon r. So here as r increase it will decrease, so outside the solenoid it will decrease with r. So these relation you must remember. Question can be framed from this. Let's see, if you have a small ring only, then how it will change, means B is changing as B naught cos omega t z cap direction. Then what is the electric field? So relation will remain same as in the solenoid case, but let's see, E dot dl will be this. So again E 2 pi r will be given by, inside we are seeing, so it will be minus B naught, again dB by dt will give you B naught minus sin omega t and omega, so it will be minus plus, and this is pi r square, that area, and it will be equal to 1 upon B naught omega sin omega t r. So here E is again proportional to r, so you must remember this case, and direction will be phi cap. So this will remain same as solenoid. So you must see that inside it is proportional to r and outside it is proportional to 1 upon r. So that is you need to remember. Now let's consider there is solenoid. Inside we have put a conducting ring with resistance R, and you need to find the EMF induced on this due to change in the magnetic field, and that's how the electric field will be produced and EMF will be induced. So let's see what is the EMF. So BT will be B naught cos omega t z cap inside. Find induced current in the conducting ring. So that will be, again first we need to check the what is the flux is changing, how flux is changing, then only we can see that how EMF. So phi m is nothing but B dot dA. So B is given by this B naught cos omega t, and area is pi and radius square, that is a square by 4. So again the EMF is minus d phi by dt, so it will give you, miss, you just need to take the differentiation. It will give you cos omega t will give you minus sin omega t, minus will become plus, and it will remain same, others are constant. From here you have EMF. Now our current is nothing but potential divided by resistance, so it is this divided by resistance. So this will be your current induced in the conducting ring. Now let's see the today's topic, that is inductance. So inductance is very important thing, means you have some two loops, one loop and two loop, then current in the first loop will give some flux in the second loop, and that induced flux we will study here and see that whatever flux is induced from this in this will be remain same if the same current is flowing in this, and we need to calculate the flux through this. So that will remain same, and that will be depending on M. We call that a mutual inductance. So let's see what is that. So first we need to find the flux of B1 through loop 2. So first current is flowing in this I1, and we need to find what is the flux flowing through the loop 2. So for that we need to find what is the magnetic field passing through this or over this loop. So for the magnetic field we use the Biot-Savart law. So due to the dl1 element, we need to find the magnetic field here at the dl2 with the r vector, the position vector. So it will be b1 equal to mu naught I1 divided by 4 pi dl cross r. This is dl cross r divided by R magnitude square. So this is the magnetic field here due to this first loop passing current I1, and here you will see that this magnetic field will be proportional to whatever current is flowing. So a current increase, the field will be increased and the flux will increase. So B is proportional to I1 and flux is proportional to I1 because B is proportional to flux. So flux passing through the second loop due to first will be proportional to whatever current is flowing this. So this is the law we will study. So flux in the second loop will be proportional to current in the first loop I1, and this is coefficient of constant. The constant of proportionality is called the mutual inductance, and we have denoted as M21, means inductance is 2 in due to 1. So this is called the mutual inductance of loop 2 with respect to loop 1. So let's find the value of this M21. So for that we need to find the flux. So flux in the second loop will be B1 dot dA2. So B1 is nothing but, we know from the vector potential, that is del cross A1. So whatever the vector potential at this point due to this first magnetic field, so it will be del cross A1 dA2. Now dA2 and this will be equal to, means using the Stokes theorem we can write this as A1 dot dL2. Now from here we know vector potential is given by this formula, mu naught I1 divided by 4 pi dL1 and the R magnitude. We know this formula. So we will just substitute it here, and we will see that flux will be given by, in the second loop, mu naught I1 4 pi. In place of A1 you will just write this, it will be dL1 dot dL2 R M21I. Means this will be equal to this, and just take this I1 outside and whatever remaining will be called M, because we can write M21 I1. So we'll see that now compare this relation, this relation. From here we can find the value of M21, that will be equal to, just take this I1 outside, that will remaining will be M21. So see, this is called the Newman's formula, and it shows that the mutual inductance will depend only on the dimensions and depends on the size, shape and the relative position of the two loops, and it is for the two loops. And see, dL1 dL2 means whatever, if you are finding the mutual inductance due to this loop on this loop will remain same, because it is depending on both of them. So that is the conclusion, that mutual inductance is depending on both the two loops and that will remain same for both loops. And from here we can see that if current this I1 is flowing in this way in this loop, then whatever the flux flowing through this will remain same what was the flux passing through this loop due to this one. So flux will remain same, because we can see this is the relation phi2 equal to M21 I1. So this is the current passing in this loop, and M21 will remain same for the second loop. Now let's see, this I1 is flowing through this, then what will the flux? Phi1 will be M21 multiply the I1 again, and M21 is equal to M12. So that means flux is remaining same. So phi1 will be I2 M12, means in the first flux if we find due to this one, so that will be I2 M12 and M12 equal to M21 and I2 equal to I1. That means flux will remain same. So you must remember this case, that you will need it in the questions, that flux will remain same if this I1 current is passing through this loop and you need to find the flux through this one. So that will remain same, flux will remain same. Now if you know that that flux is changing with time, now this is the way to find the flux. Now you know that flux is changing with time, then you can find the EMF also, that will be minus d phi by dt, that will give you minus m di by dt. So that is the use of this relation, that phi equal to mi, that you can directly find the EMF also, minus m di by dt. So it is simply depending on the how current is changing. So I hope it is clear to you. Let's move forward to seeing some things. So before that we need to understand self inductance also. Now see, here we see that how flux is changing in the second loop due to first. But see, due to this first loop there will be a magnetic field produced inside this loop only also. So there will be that magnetic field produce the flux in the first loop only. So that is called the self inductance. So let's see. Now it is current passing through this first loop, and there will be field due to this current in the first loop only. So if this current is changing, then there will be EMF induced in this first loop only. So that is called the self inductance actually. So let's see. Now current is changing very slowly, and that process is called the quasi-static, and means quasi-static very slowly, that it at every point it will remain constant. So very slowly it is changing. Now what is the flux through this source loop? This is called the source loop, and flux is changing also through the source loop. So flux will proportional to the current, and it will be equal to Li. So this is called the self inductance L, as we have seen for the mutual inductance. It's called the L for the self inductance. Now if you need to find the EMF induced in the loop, that will be minus d phi by dt minus L di by dt. So see this how current is changing, that will give you EMF induced, and this is negative sign, so that it is back EMF, means how the current is changing, the EMF will be oppose this current, means the change in the current, the EMF will oppose this change in current. So that's why we call it as back EMF. So I hope it is clear to you. Let's see some more things. Now you have two long and short solenoids. This is first one and this is second one, and you need to calculate the mutual inductance. So let's see how can we find. First, it is very small and it is very large, so we can calculate either way using this current on this solenoid, and we can find the flux through this, or we can just put the current on the first solenoid and find the flux through second one. So it will be more easy for us if we consider that current is passing through the first solenoid and we are checking the flux through the second one, because flux will remain same. So let's see, current is passing through the first one and we need to calculate flux through second one. So phi will be mi, so current I is flowing through the first solenoid, and it is the mutual inductance. So this is flux passing through the second solenoid. So let I flows in a long solenoid filled inside long solenoid be equal to mu naught n2I. So because of this, the current is and magnetic field inside this long solenoid will be mu naught n2I. So total flux through the short solenoid will be B into A, so that is B and area of this small solenoid, and multiply the total number of turns. N1 multiply L will give you total turns. This will be total flux passing through this small solenoid. So this will be your flux, and this will remain same. Means if the current I will be flowing in the small solenoid and you need to find a flux through this long solenoid, that will remain same, equal to this. Now from here you can just substitute the value of B, that is mu naught n2I, and you will get this relation pi a square mu naught n1 n2 Li, and now this is called the M. So that's how you can find for the two long solenoids or the one short solenoid, you can find the M, and this will be the value. Now let's consider one more case. There is a one ring and there is another ring, and this is very small, this is a little bit large, and this distance is very much large. The distance is very larger than B, and B is very large than A. So this is a very small dipole type structure, and this is a means these are two circular rings. Now if you need to find the flux because of this, then you can't calculate. So the easy way will be, we will assume that current is passing in this first ring and we need to check the flux passing through this second ring. That will remain same. What is the flux due to if current is passing through this ring, and we need to check the flux in this, so that will remain same. So we'll consider the easy case, that is current is in this loop and we need to check the flux in this second one. So flux through the small loop will be first we need to find the magnetic field at this point. So due to this ring, the magnetic field will be mu naught I B square by 2, B square plus D square 3 by 2. So this is the formula for the magnetic field due to a ring. So at distance D it will be given by this, and this is the B is radius for this. So multiply the area of this flux, so it is B multiply A, so it is pi A square. So from here we can just compare, take the I outside, so whatever remaining is called the mutual inductance. So for this kind of a structure we can find the mutual inductance. So this will be a mutual inductance, and this will remain same, and we can use that to find the flux inside this loop if current is flowing in this. So that is the use of mutual inductance. Now there are some examples of self inductance also. So if you are considering self inductance in the solenoid, so B inside a solenoid is mu naught Ni, and total flux passing the solenoid will be mu naught Ni. This is BA, and this is for the one turn, and total turns will be number of turns per unit length multiply L will give you total turns. This will be your total flux. So take the I outside, so in whatever remaining is called a self inductance L. Now coil, so this is a simple coil, and if you are put many coils above this circular coils and circular ring placed over each other, so you need to find the self inductance. So again magnetic field due to one ring will be mu naught I by, or the one coil will be mu naught I by 2R at the center, and for the n rings we will get n mu naught I by 2R. So this is B. Now total flux will be BA and the n. So B A and multiply n will give you this. So it will be mu naught n square. See, first here I multiply with n because there are n rings producing the magnetic field. That's why total magnetic field will be due to n rings. And here I again multiply with n because now you need to find the flux through n rings. So that's why we have taken as phi t equal to BAN, and again B will be this mu naught IN by 2R, and it will give you n square here. So n square A by 2RI. So this will be your L. Now there are one more example, that is coaxial cables. So there are two cables and current is passing, means flowing on the surface like this, and here it is passing through this, and magnetic field inside these means coaxial cables will be passing through this, coming outward and going inward here. So it is like this. So we need to find the total magnetic flux and the self inductance in this case also. So B dot dA, so B here will be given by, means it will be mu naught I by 2 pi. You are using the Ampere circular law, we can just see that this current is I, so it will be B dot dl equal to mu naught I. So B is distance is R, and we need to consider this complete area. So first let's assume this small dr distance and this R. So dr and this length is L, so LdR will give you this area. So LdR multiply the magnetic field is mu naught I by 2 pi r. So this is the flux through this small loop. Now to integrate, we need to integrate from A to B for this complete area. So that will be given by this, means integrating from A to B, 1 upon r dr will give you log r and log b by a. These other terms are constants. So take the I outside, whatever remaining will give you self-inductance. So this is the case, and why we don't consider this lower area, because here the magnetic field will be going inward. If you consider the complete area, net flux will be 0. So that's why we need to calculate only this area. So there is one more case remaining, and then we will see the 4 Maxwell's equation in next lecture. So thank you everyone.